Hello everyone. Now we have to discuss the next concept, that is analysis of balanced three-phase system. So what is balanced three-phase system? Means if sum of voltages and currents, whether they are phase quantities or line quantities, but the sum of those voltages or currents is equals to 0, then only the system is said to be balanced. Okay, but vice versa may not be true. Means if with respect to any case, if the summation of voltage or current is equals to 0, means those voltages or currents need not be equal. But for a balanced system, the sum of voltages or current should be equals to 0. Okay, first we have to write the statement. For a balanced system, the sum of voltages or currents must be 0. Okay, must be 0, but vice versa may not be true always. Okay, then let us say here I am considering some current, right? The sum of these currents 0, like that we are, that's it. Okay, then balanced system means what? We have balanced source and balanced load, right? Balanced three-phase system. In the system we have what? Source and load. That is, we have balanced source and balanced load. Right? Source means what? Only we are dealing with voltage only. Three-phase voltages are balanced. Right? Which means three-phase voltages, whether they are line or phase, which are balanced only. But coming to balanced load, which means what? Impedance load, right? Balanced load means what? The load should be impedance load, whether it is series RL, parallel RL, whether it is series RC, parallel RC, maybe resistive load also, that is impedance load. That is balanced load means what? Impedance load means what? Three-phase load currents are balanced. This is very important point. Three-phase load currents are balanced. That's it. So balanced three-phase system means what? Balanced source, balanced load. So source means what? We can able to get the EMF, means what? Three-phase alternators. For example, 11 kV of voltage is nothing but from three-phase alternator, that is three-phase voltage, which are balanced with respect to balanced source. But coming to balanced load, how many types of loads we have? Simply we can call them as impedance loads, right? Means load means what? Current. So three-phase load currents are balanced. That's it. And one more important point, source is not responsible to decide the system is balanced or unbalanced. Only load can take the responsibility to give the clarity about whether it is balanced or unbalanced. Only it should be depends upon load. That's why we can call it as balanced three-phase load, right? Only load can be responsible to give the clarity about the system is balanced or unbalanced. Okay, we can write that point. Source is not responsible to decide the system is balanced or unbalanced. Okay, only load can take the responsibility to give the clarity. Whether it is balanced or unbalanced. With respect to load only we have to say, that's it. If the system is balanced means what? Load currents are balanced, right? That is, balanced load implies what? Balanced load implies what? Impedance load. Should be balanced. If the impedance load is balanced, which means what? Load currents are balanced. That's it. Okay. Now let us consider, for example, here I am considering voltages. With respect to voltage, I am going to explain. Let us consider three-phase voltages or current. Okay, phase voltages. Sorry. Let us say VR at an angle 0, Vy at an angle minus 120, Vb at an angle minus 240, right? So we have voltages like that, impedances like that. The impedance in R phase, for example, mod ZR at an angle phi R, right? Like that, ZY mod ZY at an angle phi Y, like that ZB, which is equals to mod ZB at an angle phi B. Okay, then we have voltages, we have impedances, we have phase voltage, like that we have phase impedance. Then what about the current, phase currents? Therefore phase currents, that is IR, should be equals to what? VR at an angle 0 by ZR at an angle phi R, which is equals to what? VR by ZR at an angle minus phi R, right? Like that, IY, which is equals to what? Vy ZY at an angle minus 120 minus phi Y, like that IB is equals to what? Vb by ZB at an angle minus 240 minus phi B. That's it, right? So load currents, when these load currents are balanced, we have I phase at an angle minus phi R, IY, I phase at an angle minus 120 minus phi Y, IB, I phase at an angle minus 240 minus phi B. That is, load currents will be balanced only when what? If IR should be IY should be equals to IB, then only load currents are said to be balanced, right? For balanced currents, we know that for a balanced system, all the three currents must be displaced by 120 degrees. So to get the balanced system, all the three currents should be displaced by 120 degrees. We all know that this phase current R is at an angle minus phi R, like that Y minus 120 minus phi Y, like that IB minus 240 minus phi B. So to get the balanced load current, the phase angle should be equals to each one of them. Phi R should be equals to phi Y, phi Y should be equals to phi B, or they are said to be 0. They are equal, or the phase angle between those two currents should be equals to 0. Means what? Phi R, phi Y, phi B should be equals. That is the best condition, right? We know that phase voltages are displaced by 120. That's it, right? So to get the balanced system of load currents, obviously the phase angle with respect to impedance should be equal for all three phases. Now we have to write that point. To make all currents balanced, the angle produced by impedances in all phases must be equal. Then only we are having balanced load currents. That is, phi R should be equals to phi Y should be equals to phi B, right? Then only we are having balanced load. Balanced three-phase system means what? Load can take the responsibility to tell whether it is balanced or unbalanced. Okay, to get clear idea, I am considering phi R, phi Y, phi B, which is equals to 30 degrees. Okay, say for example here I am considering 30 degrees. Then what about IR? See, IR is what? VR by ZR at an angle minus 30 degrees, like that. IY is what? V by ZY minus 120, sorry, minus 150, like that. IB is what? VB by ZB at an angle minus 270. See, at any case, the angle between IR and IY is what? 120. IY, IB is what? 120. Between IR and IB is also 120. So they are displaced by 120 degrees apart. Therefore, we can write here. From this example, we can observe that three phase currents must be displaced by 120 degrees apart. Therefore, all currents are balanced. Clear? This is the perfect analysis. Okay, that is for a balanced load currents, for a balanced load current, the impedance must be equal. In addition with that, phase angles. That's it. Here we can write one important note point, that is, so impedance must be same, that is phase impedance only, not the total impedance. So the impedances are always taken per phase. In this concept, the impedances which are taken per phase only. There is no such quantity as line to line impedance in the concept of three-phase system. There is no term called as total impedance, as impedances are always taken per phase only. Okay, we are not considering the total impedance. There is no term called line to line impedance, only we have to consider per phase impedance in the analysis of three-phase systems. Okay, that is very most important point. The impedances are always taken per phase only. There is no term called line to line impedance. Okay, that is, there is no term called line to line impedance means what? Total impedance. Only we have what? Impedances are always per phase only. That's it. Because this is the perfect analysis. Okay. Now we have to write the properties of balanced system. The properties of balanced system. First one, first point is waveform is perfectly sinusoidal. Sinusoidal. Okay, that is in terms of magnitude and phase shift of 120 degrees. Second point is what? Current flowing through each phase is same. Each phase is same. Next, third point is no current flows through neutral, because the summation of all currents should be equal to 0. Obviously, if we consider star connection, in star connection only we have neutral. If summation of all current should be equal to 0, there is no current through that fourth wire, right? There is no current through neutral. Fourth point, power loss is very low. Power loss is very low. This is about three-phase balance system. What is three-phase balance system? In three-phase balance system, the summation of total voltages or currents, whether they are phase quantities or line quantities, those summation should be equal to 0. So the load can take the responsibility to tell whether the system is balanced or not. So to get the balanced load currents, always the impedances in respective phases should be equals to 0, should be equal in addition with that phase angle. That is, the phase angle in every phase should be equals. Then only you will get the balanced load current. Okay. Now we have to write the summary of balance system with respect to all types of currents: line currents, phase currents, line voltages, phase voltages. Okay. The first one is star connection. Later we will discuss delta connection. Okay. Summary. Okay. Here we have what? Star. Here we have what? Delta. Okay. Here the first point is what? IR, IY, IB, which are nothing but what? Phase currents in case of star connection, which are nothing but what? Line currents, right? Therefore, I phase, which is equals to IL. In this case of delta connection, VRY, which is equals to VYB is equals to VBR. They are nothing but what? Phase voltages, nothing but line current, line voltages. Therefore, summation of this currents IR plus IY plus IB, which is equal to 0. Like that, in this case, VRY plus VYB plus VBR, which is equal to 0. That's it. That's why IN should be equals to 0. This is very important observation. That's why we don't have any neutral voltage in case of, this is delta, right? There is no neutral connection in delta. That's why there is no neutral connection in delta. That's why Vn should be equals to 0. Okay. Next, that is, what is that meaning here? VRY at an angle 0 plus VYB at an angle minus 120 plus VBR minus 240. That is the meaning. Okay. Those three phase voltages are displaced by 120 degrees. Like that, in this case also, IR at an angle 0, IB at an angle minus 120, IB at an angle minus 240. Okay, this is about phase quantities in star, like that in delta. Next, second point, star, delta. Second point is what? We know that VL, which is equals to root 3 V phase. In this case, IL, which is equals to root 3 I phase. This is about second point. So In this case, VR, VY, VB, which are nothing but what? Phase voltages, right? Phase voltages. Therefore, VR plus VY plus VB should be equals to 0. That is, VR at an angle 0, VY at an angle minus 120 plus VB at an angle minus 240, which is equals to 0. That's it. Coming to this, we have IR, IY, IB. Those are nothing but what? Line currents, right? That is, sorry, first we have to write phase quantities. Later we have to write these are nothing but phase currents. That is, the summation of these three currents should be equals to plus IBR, which is equals to 0. That is, IRY at an angle 0 plus IYB at an angle minus 120 plus IBR at an angle minus 240, which is equal to 0. This is about phase voltage in star connection, phase currents in delta connection. Now, line voltage in star, line currents in delta. Third point, right? That is, in case of VRY, VYB, VBR, they are nothing but what? Line voltages. In this case, line currents are nothing but what? IR is equals to IY, which is equals to IB. They are nothing but what? Line currents. So, summation of these three currents equals to 0. That is, VRY at an angle 0, V by B at an angle minus 120 plus VBR at an angle minus 240, which is equals to 0. Means like that, IR plus IY plus IB 0. Therefore, IR at an angle 0, IY at an angle minus 120 plus IB at an angle minus 240, which is equal to 0. This is about, sorry, line voltages, right? Always line voltage leads phase voltage by 30 degrees. So, we have to provide the angle, not 0, plus 30 here, plus minus 90 here, minus 210 here, like that. I forgot that point. Here we have what? Plus 30 degrees. Here we have minus 90. Here we have what? Minus 210 degrees. Here line current lags phase current by 30 degrees. That's why minus 30. Here minus 150. Here minus 270. That's it. Okay. What is the reason? Line voltage leads phase voltage by 30 degrees. At any case, plus see, the phase displacement between any phasor is 120 degrees. That we have to check first. If that is satisfied, all are balanced. See, between 30 plus 30 minus 90, 120, minus 90 minus 210, obviously 120. See, in this case also minus 30 minus 150, 120, minus 152 minus 270, 120. So, all are balanced. Here the condition is what? Line current lags phase current by 30 degrees. This is the analysis of three-phase system. Okay, these are the important summary points. So, how to decide whether the system is balanced or not? It should be totally depends upon the load, three-phase load, that is impedance load. If the impedance is same with respect to all phases means all phases should be displaced by 120 degrees, then only the load currents are balanced, then only the system is said to be balanced three-phase system. Okay, that is the summation of all quantities of voltages or currents should be 0, then only the system is said to be balanced three-phase system.